Hello, class, and welcome to lesson 6.2. Today we're taking a look at some continuous probability distributions. Just making sure I'm recording here. Give me 1 second. Yeah, I'm good. Okay, hopefully that'll disappear in a second. Let me go to one page and come back. Okay, there we go. All right, so today we're taking a look at some continuous probability distributions, which is what we call normal distributions, okay? And we're going to be able to identify situations that give rise to common distributions. So we're taking a look at a whole bunch of different distribution types and how they graph looks and how they relate to the mean, median, and modes. All right, so let's take a look at example one. So example one, telemarketing firm analyzed the length of time it takes employees to spend engaged in a sales call. Okay, I will tell you one job I could never be as a telemarketer. Okay, so results are shown and are rounded to the nearest minute. So if they're rounded to the nearest minute, for example, if we're taking a look at 4 minutes, that really represents. So if it's rounded to the nearest minute, 4 minutes really represents like 3.5 to 4.5. You guys okay with that? Okay. And normally we do this as a class, okay? And because it's 3.5 to 4.5, therefore our data is continuous. So that goes with our title here, okay? Awesome. Okay. So what we want to do is take a look at developing the negative frequency. So just remember, this is our x and this is our y, and in order to take a look at the frequency, we've got to take a look, well, for example, at 1 minute, which is really half a minute to 1.5 minutes. Okay, not sure what they would do if it was, 0.2 minutes, which is probably me. Say hi, you don't have permission to call me, and I hang up. So that's interesting to note. Again, that'd be an assumption you'd have to make, right? So we have a frequency of 15, but out of how much? So what I need you to do is add up all the frequencies, add them all up, okay? And what do we have a total of? So we have a total of 100. Good, that makes life easy. So you would say 15 over 100, plug it in your calculator, and that's going to be 0.15. So that means you have a 15% chance of getting engaged in the first minute. I'm impressed. That's pretty good for this company. Okay, and so you do this again, so you go 12 divided by 100, might not even need the calculator for that one, 0.12. Again, you should just be able to use your math and move your decimal over 2 spots, okay, to get your relative frequency. Makes it easy when your total's out of 100, folks. Okay, so we just write these in. Don't forget this one, watch this one, 0.05, 0.02, and 0.03. Okay, awesome. Now it says to construct a relative frequency diagram, which I have already done, okay, just for you, and then to sketch a smooth curve that is a good fit for for the data. Okay, well, you'll notice here that there is a trend that goes down and back up, and that's okay. You're going to get this, okay? All right, and remember, it's a smooth curve, right? So you wouldn't want to go up and down. You just want to have some type of hump or come to a maximum and then go back down. All right. So we need to figure out the mean call length. Okay. Well, what do we have to remember is we have to take a look at, we know it's a total out of 100, but we got to do a lot of work before we get that. Okay. So up on top, we've got to take a look at each frequency times the number of what? Minutes. So I'm going to go, and you might need a line or two to do this. So I'm going to go 15 times 1, right? Plus the next one, which is 12 times 2, plus 3 times 18. Or sorry, I should keep the pattern 18 times 3. Just keep that pattern going. And keep doing it for the whole thing. So plus 4 times 22 plus 5 times 13 plus 6 times 10 plus 7 times 5 plus 8 times 2, almost done, plus 9 times 3. Okay, everybody okay with that? Oh, I guess I switched. Sorry, I switched. Anyway, it still give you the right answer. Okay, so just my order was in the wrong order, I guess. Okay, so taking a look, ladies and gentlemen, you find the mean, plug it in your calculator. You're going to get 3.84. What does that mean? That means that therefore the average call length, oopsie, what happened there? Length is 3.84 minutes. Okay? Awesome. Everybody okay with that? All right. So here's again what we want to do. Remember, we are now dealing with continuous random variables, like number of minutes in this case. And things can get measured. It's things that can get measured. So we have decimals or fractions as part of our answers. Okay, what does that mean? Yes, that means a call can last 3 minutes and 45 seconds or 5 minutes and 2 seconds, okay, because it's measured. Okay, so what we want to take a look at is probability density, the probability per unit of continuous variable, and that is the red curve on the graph. Okay, so it's the curve. So the density deals with the curve on the graph. The probability itself is what's under the graph. So just make sure you know the difference between the density and, I'll just make sure we highlight that whole thing, the density and just the probability. All right, let's take a look at different types of continuous distribution shapes. Some of these you should hopefully have heard of before, and some of these might be new. Okay. These are actually, I actually discuss these in like grade 11 college. I do it in grade 12 as well. So this is something maybe not in the university stream, but you may have seen this. Grade 11 college, we do a statistics unit, so we do actually deal with this. All right, so let's take a look at continuous distribution shapes. Symmetrical means that the left and the right side are equal, or there's a mirror image. And the first one we're going to take a look at is normal distribution, or bell curve. Okay, so a bell curve kind of makes it look like a bell. Comes up to one module, one mode, and comes back down. Okay, and when it's perfectly symmetrical, you will find, just one second, sorry, I've got the phone ringing here. Hello, sorry about that, guys. I just had a quick phone call. All right, so we're taking a look at distributions. Remember that when we take a look at symmetrical, the bell curve, the mean, mode, and median are all at the same spot. Okay, so the mean, mode, and median are all together. Okay, and don't forget that x is our random variable, and this is where our mean would be for the random variable. And again, on the y, it's frequency. Okay? All right, please do me a favor, guys. I don't want to waste time in the video, but ask me about how in university I wrote the bell curve, because I want you to make sure you're aware of that, because that might happen to you. It's happened to many people that I've talked to. All right, and that's dealing with marks. So just ask me, Miss R, tell me about the story about the bell curve, and I'll tell you guys. All right, so a uniform distribution, again, our random variables on the x, our frequencies on the y, okay, and a uniform means that it has equal distribution. So we take a look at a die, folks, and we roll a 1, or we roll a 2, or we roll a 3, or we roll a 4. They all have the same result, right? So it's the same probability. So you're going to see a horizontal line, okay? Okay, and when we take a look at the mean is in the middle, okay, so they all have the same probabilities. That's why they all have the same frequency, okay, so they all have the same mode. They're all equally likely. So that's a term to make sure you know. Equally likely. All right, now, bimodal distribution, you guys, this is going to look funny when I'm done, and I'll tell you, well, you'll know as soon as I start drawing it. So bimodal means we have two modes. So it looks like this, okay? And when I teach these students and I put on the modes, people tend to represent something about this, and you guys can figure out what it looks like. And it's two modes. Okay, so we have two higher hills here, folks. And don't forget that when we take a look here, that we've got our random variable on the x, and we've got our frequency on the y. Okay. And when we take a look at this diagram, just remember that the median and the mode are going to be in the middle. Okay? All right. So those are three types of symmetrical. So notice if I put a mirror image, let me just quickly do this so then you guys get what I'm talking about. Okay? So, there we go. So if I take this and I put it right here, it should be roughly a mirror image. It doesn't have to be perfect, but pretty darn close. Okay, I put the mirror image here, mirror image here. All right, I'm going to see you later because I don't need you in here. Delete. There we go. All right, so now let's take a look at some non-symmetricals. Okay, so the first non-symmetrical is the one we did, I believe, yesterday. We did an exponential distribution. So frequency on the y, random variable on your x. And when we take a look at this, ladies and gentlemen, notice the left side, we can't put that bar in because it's not equal. And you're going to find that your median is somewhere in the middle here. Okay. The next one is what we're going to take a look as positive skewed and negative skewed distributions. So positive skewed and negative. Okay. So another name for this between positively skewed distribution, if you're looking on the internet, is going to be right skewed. Okay, for this one. Okay, so if you're looking on the website, on the internet, instead of positively skewed, you might see right skewed. Whereas if it's negatively skewed, you're going to see that this is left skewed. And I'll show you when we do the diagram, it'll make more sense. I will accept either or on your test. You can use negative or left or positive or right because they're both used. Okay, so if we have a normal distribution, ladies and gentlemen, okay, and I kind of push things this way, okay, so I push things that way, the hump or the majority of the data is going to be there, and then there's going to be what we call a tail. Okay, all right, so if we put frequency on the y, random variable x on the middle. Because we push the data, the mean is no longer right in the middle. Okay? All right? So this is the tail. So one example I could say, folks, is if we have a company and most people work on the line or in the factory, so most of the people live in this area, right? But then there's a couple CEOs or bosses or managers, they make a lot more money than everybody else. So they kind of pull the average amount of salary the other way, or the average wage this way. Okay? And don't forget that the mode is up here and it's not centered. It's not in the middle. Okay? All right. In every other example, there's either one mode or two modes that are centered. Okay. Taking a look at the other way, if I push it the other way, so if I go up to my normal distribution and I push this way this time, okay, that means I'm going to start with the tail, and then I'm going to go up. Okay? So what we notice that our mode is here. Okay? Our tail is here. Oopsie. Tail. Okay? And this is our random variable, and notice because we've pulled it that way, the mean is off the center. Don't forget frequency. Okay, so an example of this could be, ladies and gentlemen, if we took a look at workers, all regular floor employees, ignored the CEOs, okay? So everybody may be in a factory that works on the floor, okay? Most of the people work here. However, maybe there's a couple part-timers that work part-time here, or fill-in relief workers. They don't work as many hours. They pull the average. Okay, they skew the average, which makes it a left skewed. Okay, so it makes it lower than it should be. Okay, so note skewing can also occur in bimodal models as well. Okay, perfect. Let's try some examples now. Okay, describe each probability distribution. Draw a vertical line to represent the mean. Well, taking a look here, folks, this would, if I covered up this part, it would kind of look normal distribution, but notice that there's a tail here, okay? So the tail is going to mean that that is a negative skewed distribution, okay? And or you could say a left skewed distribution. I'm okay with that. Just think on the it's going the negative way on an integer line if you're not sure. Okay, and where would the mean be? Well, that tail pushes the mean this way, so the mean's probably here, not off the center. Okay, now taking a look at this, ladies and gentlemen, we have 1, 2 modes. Okay, so what does that tell us? That this is bimodal. Okay, and if it's bimodal, it's symmetrical, and the mean is in the middle. Okay. Now this one's a little bit different. Hopefully you recognize there's 2 modes. Okay. But if we take a look at the end behaviors, this one has a bit of a what we call a tail. Okay, so this is going to make sure that there's a skewing, okay, but it's on the positive end, okay, so it's going to be a positive skewed, and then do we call this what? Hopefully you realize there's 2 modes, so it's going to be bimodal distribution. I apologize, I forgot to write distribution for the second one. Can you just throw a DIS in there? Awesome. Okay, one more page, and we're going to take a look at our textbook, folks. I'll take an example from there. So in our textbook, we've got an example. I've copied it right here, and it's on page 416, and it's example 1. It's an example of uniform distribution. So, taking a look at the probabilities of uniform distribution. Okay, so the driving time between Toronto and North Bay is found to range evenly between 155 to 240 minutes. Just remember, traffic and cottage traffic on the weekend plays a big role in this. What is the probability that the drive will take less than 210 minutes? Okay, so instead of giving us a table, folks, they have given us a graph. Okay, all right. So the probability density, okay, is on the x, okay, and the time is on the x, and the probability density is given. Okay, so first of all, let's take a look at what our range is. Okay, so our range in our box, remember guys, is the what? Larger value subtract the lower value. Good. Hopefully you remember that. So range equals 240 subtract 195. Grab your calculators if you need it, and that's going to give you 45. Okay. All right. So if we take a look at this, okay, and that's the whole box, right? If we take a look, that's one whole box, okay? So that's going to be, so probability equals 1 divided by 45, okay? So that equals 0.022. And that is shown right here. So we're just showing you where that came from, okay? All right. So now, just in case you were wondering where that came from, okay? All right, so let's take a look, folks, at the random variable. What are we looking at? It's the driving time. Okay, and we want to know what the probability is taking less than 210 minutes. Okay, so probability where x is less than 210 minutes, okay? And what do we need to do? We need to find 2 tens. So 2 tens here, and that's why that diagram gave it. We're going to shade this part, or make sure we know that's the shaded part, okay? All right. So to do this, remember, it's the area. To find the probability when it's less than 210, it's the area shaded in my little stripesies. Okay, so to find the area, you have to take a look at this part. Okay, 0.022. Subtract the difference in that area, so that would be 210. I'm sorry, I apologize. The 0.02 is this 0.022 is that part, my fault, sorry about that. Subtract the difference, which is the top part. So that's 210, subtract 195. Okay. Plugging that in is 0.022 times 15, and you get an answer of 0.33. So what does that mean? Therefore, there is a 33% chance that the drive is less than 210 minutes. And hopefully they're not talking about long weekend cottage weather. I grew up in Barrie, and I know that makes a big difference. Okay, so taking a look, folks, here's your homework, page 419, numbers 1, 2, 4, and 6. Have a fabulous day.